Reminder that we're going to have the first midterm next Thursday. Later, Dr. Eldridge and myself, we're going to send out more messages about the midterm. But roughly speaking, it's going to cover lecture 1 till lecture 8, which is what we're going to cover this Thursday on the binary search tree. Okay. All right. So last time, we talk about sorting an array, and we talk about the merge sort, which has asymptotically the optimal time complexity, which can sort a list of numbers in n log n time. Okay, and before that, we also talk about if we're given a sorted array, then we could search for an element efficiently using the binary search procedure. Okay. Now, we also mentioned that once you have an array already sorted, then you can do many things efficiently. Okay, for example, if you want to select a specific number with a certain rank in the array, you can just access this. If you want to select the smallest one, you just go to the first entry in the array, or the largest one, that's the last entry in the array in constant time. Okay, but today what we want to talk about is that what if without sorting the input list of numbers, we would like to have efficient procedure to select a specific number with a certain rank. Okay, so this is so-called a select problem. Okay, so for example, how do we find the median of a list of unsorted list of numbers quickly? Okay. Now we mentioned the median problem before, and we already described, for example, one way to solve the median is that essentially you solve this as an optimization problem. That's the number whose total sum of this and to all others is smallest, okay, in quadratic time. And now, if you're watching this offline, you can also just pause and think. Based on what we already learned, how fast can you think you can find the median of n numbers? Is the n squared the best you can do, or can you do better? Okay. All right. So as I said, the type of question we're going to ask now is the so-called order statistics. So what is it? Well, given a set of n numbers, okay, the case order statistics is basically the case smallest number in this collection. Okay, sometimes I also refer to this as that this number has rank k. Okay, the rank is its position in the sorted list, basically. Okay, so for example, here are some common ones that we've seen before. The first order statistics is just the smallest number, the minimum. And the n's, if you have n number, then the n's order statistics, that's basically the one who is the largest because the rank of it is n, okay? And the n over 2's order statistics, that's basically our median, the one whose rank is in the middle. So it's basically n over 2's smallest number in this entire collection. Okay, sometimes if we talk about the P's percentile of your data, that essentially is referring to basically the Pn over 100's order statistics. Okay, so we've seen this before, but although we're not talking about in this specific language. Okay, so what is the problem that we want to solve? Well, the so-called select problem, namely, we're given n numbers stored in the array A. Okay, and I give you order k. Okay, you are supposed, oops, it should be order k going from from 1 to m, and the goal is to return the case order statistics of A. Okay, so for example, if I give you an array A and the k equal to 1, that means that you are supposed to return the smallest number in this array. Okay, if I give you k equal to n over 2, then you're supposed to return the median of this list of array. Okay, so that's what we want to do. We want to be able to do this efficiently. Okay, and now the special case that I mentioned just now, like k equal to 1, means that we're going to look for, we're finding the smallest one, the minimum. K equal to n is the largest. Okay, so for this, how fast can we do this? Well, if you think about it, we've seen this before. The smallest one, we can just linearly scan the entire array while remembering which one is the smallest. So we can do this in order of n time. Okay, the same for the largest one. Okay, but then you ask yourself, does the same strategy hold for other k, say the median? Okay, can you just remember who is the middle? Well, we cannot do that so easily anymore because at the beginning we don't know who is the who could be the candidate for the middle one. Okay, so the strategy has difficulty handling general K. Okay, so how do we solve this select problem? Okay, now remember that we always say that given a problem, the first approach you can have is that just think about what would be the straightforward approach you can think about. Okay, so we've seen, for example, selection sort before. Okay, and it's very easy to modify the selection sort idea to be an algorithm to return the case order statistics. Okay, what do I mean? In particular, remember, here's the algorithm for selection sort. And remember how the algorithm works? The algorithm basically that it goes through the array in n-1 rounds. At each round, it finds that what is the small, it repeatedly finds the smallest number in the remainder of the array. Okay, so after the first round, you find the smallest one. After the second round, you find the second smallest one, and so on. Okay, and in the end, if you do this after n-1 round, your entire array is sorted from small to large. Okay, so here we only care about finding the case smallest one because we want to find the order statistic, case order statistics. Okay, which means that we can just modify this algorithm because the algorithm repeatedly retrieves the smallest one. So now we can just run this in k rounds because after that, we know that we already found the case smallest one. Okay, then we simply return the current, the case element. Now note that our array is in the index starts from 0. Remember the array, the indices usually start from 0 to n-1, while the case order statistic k starts from 1. That's why there's a shift in the indices. Okay, so the index k-1 in the array A is the case element. Okay, so basically we use selection sort. We just repeatedly retrieve the smallest one. We do this k times, we find the case smallest one. Okay, so all right, the procedure is rather simple. So what is the time complexity? Well, by each time we need to repeatedly find the minimum, and finding the minimum takes n time, linear time. Okay, and we'll only need to do this k times. Okay, as such, the algorithm takes time k times n. So I leave this k here because in some sense that now, remember like in our earlier homework, now basically we have two variables, both k and n input variables, input size. Okay, so now if you are looking for if k equal to 0, sorry, equal to 1, then this algorithm is linear time. Okay, and if k equal to say n/2, which is our median, then this algorithm actually takes quadratic time. Okay, so to solve. Okay, so it's not super efficient. For most of the k, it can be for more than half of the k, it's a quadratic time algorithm. Okay, so now you ask, can we do better? Okay, well, on the other hand, okay, we've seen some efficient algorithm. Okay, remember we've seen sorting algorithm. What if I first sort the input array? And the sorting can be done if we use merge sort. Then the sorting can be done in n log n time. Okay, but once I have this array sorted, okay, all of them are already ordered. The case order statistics is simply the element, the case element in the array, which is the one with index k-1. Okay, so we simply return a k-1. That's it. Okay, so this step only takes constant time once the array is sorted. So what is the total time of this approach? The approach is the sorting time plus the time to return step 2, so that the total is still the sorting dominates. Okay, so by first sorted array, then we can actually improve the time complexity from previously worst case n squared to n log n for any k. Okay, it doesn't matter which index, which rank you're looking for. Okay, so this is much more efficient. Okay, and now the question now is that, can we do better than sorting? Okay, is sorting really needed? Okay, and that's what we want to do. Okay, so what I'm going to do now is that I'm going to first describe you an idea behind an algorithm called QuickSelect. Okay, and at the beginning, you'll see that this may not be that efficient yet, but then we're going to make a change to it to make it efficient in expectation. Okay, so that's what we're going to do. Okay, all right. So in what follows, I'm going to use pseudocode to write the algorithms, okay? But as a convention, remember that array indices start from 0. So the and size n array, the indices are from 0 to n minus 1, okay? So just same as your Python, okay? I'm using pseudocode because number one, it's good for you to be able to read pseudocode. Number two, many of this idea looks cleaner when you use the pseudocode presentation. Okay, but you can easily change every code I have here to the Python code. Okay, all right. Now remember, here's the problem we want to solve. The select problem where the input is a list of n numbers, an array of n numbers, and an order k. And our goal is to return the case order statistics of this array A, namely the element with rank K, okay? So we mentioned earlier that we could do sorting. We sort all the elements in A in n log n time and then find this one efficiently, okay? And we want to know whether we can do better, okay? So to understand that, first you ask yourself the question, what are the redundancy in sorting, okay? So in sorting, essentially, we need to figure out the relative order among all pairs of elements, right? Because once you have it sorted, then given any two elements, you know their relative, who is bigger, who is smaller than, okay? So now that's where the redundancy comes from, okay? For example, if I have two numbers, both are going to be smaller than the target, the case order statistics. Okay, so let's say you want to find the median. Okay, now you have two numbers, their rank, their order are both smaller than the n over 2. Okay, so they're both smaller than the median. Then I don't really care what's their relative order. I don't want to spend time to compare them, right? Because it doesn't matter. As long as they're both smaller, I know that they should be added to the count of those that are smaller than me. Okay, so I don't care about their relative order. Okay, so this is a part of kind of redundancy from the sorting algorithm. Okay, so intuitively, if we want to do better than sorting, we need to somehow remove this redundancy to be more efficient. Okay, the question, of course, is that how do we really achieve that? Okay, how do we leverage the sort? Okay, so let's start actually with the following exercise. Let's say that I give you n doors, and behind each door there is a number. And so for now, let's say your goal is to find the largest number behind the door. Okay, and what you can do is that you can ask to open a specific door. Okay, and now here's the one extra ability that we're given. Suppose there's an oracle. Every time you ask to open a specific door, okay, and then we have an oracle that tells us that for which doors are smaller than the number that you just opened and which doors are bigger. Okay, so suppose we are equipped with this extra power. Okay, can we now, how fast can we find the largest number? Okay, so just look at an example. What I mean, let's say that, let's say I take the following strategy, okay? I look at let's call this what the oracle does. Let's call this a partition operation. Namely, given the current door, the number that I opened, the partition operation would then divide all the numbers to those are smaller than me and those are bigger than me. I don't know what they are, but I know this is smaller than me and this are bigger than me. Okay, so this is called a partition operation. Okay, so now I equipped this partition operation. So here is the strategy I'm going to take. I'm going to first open the last door, okay? So I open this last door and the number is 20, okay? Now I ask the oracle, the partition oracle. Now what the partition does is that it tells me that these two doors, I don't know their number, but they're smaller than me. And this are all bigger than me, okay? So that's what the partition does. So if you think about it, what does this tell me? That in fact, what the partition is doing is that it actually put a 20 in the correct position in the sorted order, because everything to the left is smaller than 20 and everything on the right are bigger than 20. So if you're going to supposed to sort them, then this is a correct position for 20. Okay, all right. But what do we don't care about sorting. What do we want to do? We want to find the largest number, right? So now, what do I do next? Do I still need to check D and E? Well, I care about the largest number. So the largest number, the rank is n, clearly bigger than what the rank of 20 is. That means that I can now ignore D and E. I only need to continue with the right side of it, because what I care about, what I'm looking for, is bigger than the rank of 20, because I'm looking for rank n, right? So after the partition, to move forward, I could eliminate part of the array. You see, I don't need to compare relative order between D and E anymore, because I know they're going to be not needed. They're not going to be the number, contain the number I'm looking for. So now I'm going to recurse on only the right part. Okay, so what do I do with the right part? I repeat. Okay, let's say that I still do the same strategy. I say now, let me, again, within the right part, let me open the last door. That's my strategy, okay? So I open the last door. Again, I ask my oracle, say, please do the partition operation for me. So what the partition is doing is that now it put 84 in the correct position. Namely, we know that this is smaller than 84 and this is bigger. B, the door B is bigger than 84. Okay, so we don't know what those numbers, and we don't know whether their relative order is right, but we know we put 84 in the position such that everybody to the left is smaller than it and everybody to the right is bigger than it. Okay, so that's what we do. So what's next? Well, we are looking for the largest number whose rank, right now 84 is in the rank 1, 2, 3, 4, 5, 6. But we're looking for rank 7. That means, again, we need to go to the right. But fortunately, now in the right, there's only one number left. That must be the largest one. So we simply now open the last door and return. This has to be the largest number. Okay, so that's what we do. All right, so that's the idea. Again, what was the idea? What we do is that at any moment, I first open some door, and let's say I always open the last door of the portion I'm looking at, okay? So using this number, I call the partition oracle procedure, which kind of divided all the numbers in the array to those that are smaller than me and those bigger than me, okay? Then depending on what I'm looking for, in this case, I'm looking for the largest. Now I can basically ignore part of those numbers. Okay, so for example, when we're looking for something bigger, now we can ignore everything to its left because those are smaller. Okay, so that helped me to quickly eliminate a lot of numbers that cannot be candidates. Okay, so I can quickly shrink to the portion that contains my target. Okay, so that's the idea. All right. Okay, all right. So now, this is what I described just now is looking for the largest number, okay? But can we generalize this idea to looking for any rank, any order statistics for any K, okay? So again, let's assume this oracle, this partition procedure is already given. So let me be a bit more precise. What is this partition procedure, okay? So what the partition procedure is doing is that you're given an array A, okay, and let's say that you're looking at the S to T minus 1, this portion. Okay, so you consider the subarray from S to only within this range. Okay, and what the partition will do is that it's always going to use. So let me draw this nicely. So this is T minus 1. So it will always, we're considering this shaded portion, it's always going to use this element as a pivot, okay? And we're going to now partition this red portion into a new so that the green one now, we're going to partition the red portion so that everyone to the left, this is our pivot, so that everyone smaller than the pivot P, so this value is P. Everyone smaller than P are going to be to the left of this green new position, and everyone bigger than P are going to be the right. Okay, so we're going to change this red portion, partition it so that P is in the correct location. It separates those smaller than it and those bigger than it. Okay, so that's what this partition is doing. And what it returns is the position of this new pivot, the new position for this pivot. Okay, so the indices in the array +1 basically. Okay, so that's our oracle. Okay, we're going to see how to implement the partition later, but this is what the partition is doing. You're given the pivot, which is the last element in the current portion. Then you split the current array into the parts that's smaller than it to its left and bigger than it to its right. That's it. Okay, all right. So assume we have this partition procedure already. How do we generalize the idea we just mentioned to select an arbitrary rank K in the array A? Okay. All right. So what we're going to do the following. You are given this array here that you want to select the specific rank or the status K. Okay. I'm going to first, using call the partition oracle. Okay, remember that's going to take the last element as a pivot. Okay, and then it's going to divide the array into the portion. These are all the elements smaller than P, and these are all the elements bigger than P. Okay, so I'm going to first call this. Okay, and what's next? So now my array is nicely divided. I don't really, it's nicely divided into all the pink number who are smaller than pivot P and all the green ones who are bigger than P. Okay, and the position of my pivot is basically it's index M in the array, which means that the order of it is actually M+1. So the pivot is in the correct position now, okay? And what is its order? Its rank. Its rank is basically M+1, okay? So we are looking for, our goal is to look for the element with rank K, okay? If K equal to M+1, what does it mean? That means that the rank K element is exactly the pivot. We found it. We simply return AM, which is the same as the pivot. Okay, so we found it. Okay, so in other words, after partition, the thing with the information we already have is that we know where is the position of the pivot P if it's in the sorted array. Okay, so we basically now P is in the correct position now. Okay, so we know its own order. Okay, which is M+1. Okay, so if the rank we're looking for happened to be M+1, then we now found it. That's simply the pivot we returned. Okay, so that's the good case. Okay, and remember this is smaller than P, this is bigger than P. Oops. Questions? Feel free if you have questions. Okay, now if it's not the case, if the rank we're looking for, K, is smaller than the pivot's rank, okay, it's smaller than M+1. What does it mean? What do you think it means? Well, that means that it has to, the rank is smaller than the pivot. That means it must be smaller than the pivot. That means that it has to come from the left of this part of the array now. Because everybody smaller than the pivot now is to its left. Okay, what this means is that I can safely ignore everything here. Okay, the rank we're looking for is smaller than the rank of the pivot. Then we can ignore everything that's bigger than it. We only now need to continue with this little portion. Okay, in fact, we don't even need the pivot. We can continue with inspecting only this part. Okay, yeah, and that means that we could recursively run the same algorithm, but now we only focus on the part of the array from 0 to m minus 1, and still looking for the rank k there. Okay, so this is the second case. So if the rank we're looking for is smaller than the rank of the pivot, then we go to the left because we know it must be there. We can ignore the green part. Okay. Otherwise, if the rank, that means the rank is bigger than the pivot. Okay, then it's the opposite. In this case, I know what I'm looking for must be in the green portion. So I could now ignore the red, the pink part, which is smaller than the pivot. Okay, because I know what I'm looking for is bigger than the order of the pivot. So in this case, I recurse only on the green portion, which is from m plus 1 till the end of the array, still looking for the rank k. That's it. Okay, so as we see, I can, this is essentially the generalization of the idea, the example we went through earlier. Essentially, you pick a pivot, you partition the array, okay? The good thing about the partition is that after partition procedure, okay, the pivot itself, this P, is in the correct position, okay? Its index in the array basically give us the plus 1, basically give us its order, okay? So now we simply compare the order k we're looking for with this m plus 1, okay? It depends on whether it's equals to it, smaller or bigger, we can act accordingly, okay? And if it's equal to the rank of the pivot, we're done. Otherwise, we only need to, the nice thing is that we only need to go to one part of the subarray. The other part is going to be eliminated, okay? Because they're not, we know that they can be excluded, okay? All right, so this is the idea, and here is the pseudocode for what I just said. Let me just, let's just go through this quickly and see. So basically, this is just a termination condition, okay? If the subarray you're looking for is already of size 0, we're done. Or if the k is out of the range, then it's basically out of range, error. Otherwise, we run the partition operation. Note that in the partition operation, we always use the last element as pivot. Okay, the portion of the array, we use the last one as a pivot, okay? But after partition, we partition the array to be those smaller than the pivot, and those bigger than the pivot. And m is the position of the pivot, okay? The order of the rank of the pivot is simply m plus 1, because, I mean, remember the array indices has a shift by 1, okay? So if the order we're looking for equal to the order of the pivot, we're done, we return it, okay? Otherwise, if it's bigger, if the order we're looking for is smaller than the order of the pivot, that means we need to go to the left part. So this is the left part. Otherwise, if the k is bigger than the pivot order, that means that what we're looking for is bigger than the pivot. Then we go to the right part. This is the entire algorithm. It's a recursive algorithm. Okay, questions? All right. Okay. So of course, that at the top level, when we call, given the input array, we will call that A, we give the entire, we look for from 0 to n minus 1, and we're looking for the rank k, okay? So let's just go through one, look at one example, make sure that we understand the procedure, okay? Let's say that this is the input array we're given, okay? So we're given 13, 2, 5, 9, 4, 6, okay? So first, we, at the beginning, at the top level, we call the QuickSelect A 0, 1, 2, 3, 4, 5, 6, 6, and then we're looking for rank 2. Okay, that's what we're doing, okay? So what does the algorithm do? The first step is that the algorithm does partition. And remember, at this point, the partition will use the last one as the pivot. And after the partition, so this is after partition, we basically put everything smaller than the pivot to its right and everything bigger than it to its left. Okay, and those smaller than the pivot in this case is basically 2, 4, 6, and those bigger than is 13, 9. I'm missing one. Oh, 5. Okay, so this is what we have. Okay, so this is after step 1. Okay, so the pivot now, this is our pivot, is in position m equal to 2. That means that the order of the pivot equal to 3. Okay, what are we looking for? We're looking for the rank, which is 2, which is smaller than the pivot order. That means that next we have to go to the, we recurse to the left. Okay, so now we recurse to the left part, which is A, only 0, 2, and 0, 3, 0, 2, and we're looking for 2. Okay, so now we only recurse on this portion. Remember what our algorithm does is that now I use, for this portion, I use 4 as a, so the next step, the pivot. So we only recurse on this portion. Let me just write it here. And the next step, the pivot will be 4. So then we again run the partition in the algorithm, which is now only this small portion. Okay, this is our pivot. And then after the partition, in this case, nothing changes. And the pivot has its order, which is 2. And that happened to be the same order as the one we're looking for. So we simply return number 4, which is the value of the pivot. That's it. So we found that the rank 2 element, the element with order, the second order statistics in this array is value 4. That's it. Okay, so that's how the algorithm works. Okay, all right. Questions? Okay. All right. Let me just